Hello everyone, welcome to my channel Enthusiasm. Today we're going to solve this fantastic exponential and trigonometric equation. I'm going to show you the first solution. Then I will prove that this is the unique solution in the range of 0 to 2 pi. Because we have exponential functions, let's check the base first. If it's negative, then we may have an imaginary number. For example, when x is equal to 5 pi over 6, then sine x is equal to 1 over 2 and cosine x is equal to negative square 3 over 2. Put these inside the right-hand side of the equation, we get this. The index 1 over 2 means square root. Therefore, cosine x to the power of sine x is equal to square root of negative square 3 over 2, which is an unreal number. In this video, we only focus on real cases. That is, after putting values of x inside, then both sides of the equation are real. Of course, you may want to know what about the unreal case. Keep watching this video for the method of solving. Then you can figure it out. Now, we have to find the range of values of x. For sine x greater than or equal to 0, x is in quadrant 1 or 2. For cosine x larger than or equal to 0, x is in quadrant 1 or 4. To make sure that the two bases sine x and cosine x are positive or 0, we have to consider quadrant 1 only. Now, let's solve for the first solution. You can see that on two sides of the equation, the base and the exponent are swapped. If they are equal, then the equation can be solved. So why not set sine x is equal to cosine x? Then divide both sides by cosine x. We get tangent x is equal to 1. That is, x is equal to pi over 4. For general solutions, we have x is equal to 2n pi plus pi over 4, where n is an integer. But wait, how can we divide an unknown cosine x? If it's equal to 0, then the whole thing is undefined. Don't worry, it cannot be 0. Why? Because if cosine x is equal to 0, then from the equation, sine x is also equal to 0. Therefore, sine square x plus cosine square x is equal to 0. However, we know that sine square x plus cosine square x should be equal to 1. It's a contradiction. In other words, there's no problem with the solving steps, and the solution x is equal to pi over 4 is valid. Yet, how do we show that this is the unique solution? Let's look at the graphs of C1. F of x is equal to sine x to the power of cosine x, and the graph C2, g of x is equal to cosine x to the power of sine x in quadrant 1. For the endpoints, x is equal to 0 and x is equal to pi over 2, f of 0 is equal to 0 to the power 1, which is 0, and f of pi over 2 is equal to 1 to the power of 0, which is 1. Likewise, for g of x, g of 0 is equal to 1, and g of pi over 2 is equal to 0. If we just look at the endpoints of the two graphs, then the value of fx is getting larger, and that of gx is getting smaller. Let's make a wild guess. If the graph of C1 is increasing and the graph of C2 is decreasing, then they intersect at only one point, hence only one solution of the equation. It would be so nice. But is it really the case? How to check if a function is increasing or decreasing? Actually, we have a really powerful tool to do so. Right, it is differentiation. Let's start with the graph of C1. Differentiate sine x to the power of cosine x. We cannot use the power rule to bring down the index cosine x. Why? Because it's only for constant indices, and clearly cosine x is a variable. So what should we do? Well, let's take log on both sides of the equation. Using property of logarithm, the index cosine x can be moved to the front. Therefore, log y is equal to cosine x times log sine x. Now, we can differentiate both sides with respect to x. For the left-hand side, the variable is y but not x. Therefore, we have to apply chain rule in the following way. Differentiate log y is 1 over y, And don't forget the dy dx. This method is called the logarithmic differentiation. For the right-hand side, we use the product rule. Each time we differentiate a function and keep the other one unchanged. Therefore, we have cosine x d log sine x dx plus log sine x d cosine x dx. For the first term, we use chain rule again. So it's equal to cosine x times 1 over sine x times cosine x. For the second term, differentiate cosine x is negative sine x. Let's simplify this equation before we move on. Now, multiply y on both sides of the equation. To express dy dx in terms of only one variable x, we put y equals to sine x to the power of cosine x back to the equation. For the terms inside the bracket, we combine them together, then dy dx is equal to sine x to the power of cosine x times bracket cosine square x minus sine square x log sine x all over sine x. It looks quite complicated. So how do we use this to prove that the graph C1 is increasing? Let's check the signs of the terms. In the introduction, we have discussed that x is between 0 and pi over 2. Therefore, both sine x and cosine x are larger than 0. Then the exponential term is also positive. For the term in the bracket, clearly the square terms are larger than 0. So all the terms in blue rectangles are positive. Let's look at the log term. Because sine x is between 0 and 1, therefore log of sine x is smaller than 0. With an extra negative sign in the front, the whole term is actually positive. Putting everything together, we'll have dy dx is larger than 0 in quadrant 1. That means the graph of C1 is increasing. So we get our expected result. How about the graph C2? We can use exactly the same method to differentiate the function. You may want to pause the video for a while to check each step. For the graph C2, dy dx is equal to cosine x to the power of sine x times bracket cosine square x log cosine x minus sine square x all over cosine x. The derivatives of the two functions look very similar to each other. Again, the terms in blue rectangles are obviously positive. For the remaining log term, because cosine x is between 0 and 1, therefore log of cosine x is smaller than 0. So the two terms in the numerator are negative. That means dy dx is smaller than 0 in quadrant 1. The graph C2 is decreasing. Let's have a look at the two graphs drawn by computer software. The domain of C1 is from 0 to pi, that is quadrant 1 and 2, while the domain of C2 is from negative pi over 2 to pi over 2, that is quadrant 1 and 4. We can see that there's only one point of intersection, which is x is equal to pi over 4. We have used calculus to solve this amazing equation. But what if we allow unreal values in the equation? Just as we have x is equal to 5 pi over 6 at the beginning of the video? How about the unreal values of x? Let me know your thoughts in the comment section below. If you want to know more interesting problems of trigonometry, please check out the links of the videos and playlists on the screen and in the descriptions below. See you in next video.